Here with problem number 16, what we basically have is a box, and what we've done is we're folding up pieces of along the box in order to create it. And what we want to do is, part A says we want to write a formula for the volume of the box. Okay, so let's analyze this real quick. Remember, think about a box in general. Don't just ignore this picture in front of us. Just think about a box in general. That normally when I find the volume, all I need is the base times the width times the height, or length times width times height, right? So the volume is going to be, let's say, length times width times height in general. Now, when I go to look at this, now just think about this for a second. If I fold this little piece right here, if I fold that up and I fold this up, then the lid's going to go across the top, right? And this edge is going to come up and this edge is going to come up. So really, when I think of the length times the width times the height, we know for a fact the height is just going to be x. Okay, so h is just going to be x right there. The width is just what I've drawn here. It's almost like in those purple lines right here. This is just the width. That right there, and then up right here. So that's going to be our width, and then our length is just from here to here. Just here to here. Because everything else that you see right there are all flaps are going to come up, and that all represents the height. Okay? So in general, if I know that all of this base right here from left to right is 15, okay, then I can say that half of this, if I cut this right in there, wouldn't you say that's 7.5? And then over here would be 7.5. Okay, because what I have is x from here to here, which is x from here to here. Well, the base also has to be the length of the lid, otherwise the lid's not going to close on top of the base. You know, you're going to have a gap in there. So I know I can divide those two parts into equal pieces. So that length right across there, which is, well, I guess we can call it, yeah, we'll call it the length maybe, is going to be 7.5, and then I'm going to subtract off x because this left piece is going to get folded up. So the length is 7.5, the total distance across there, minus x. Or we can think of the length of the base should be the length of the height. So if that across there is 7.5, and I fold it up along the x, then it's 7.5 minus x as well. Okay. The last piece we need to then focus on is the width. Well, the width is right here. It used to be all 10 inches, but because I'm subtracting off x once and x twice, then the width is going to be a total of 10 inches, but subtracting off 2 x's. Okay, so now let's put that all together in one big equation, and we can work with that equation. So volume is going to equal the length, so 7.5 minus x, times the width, 10 minus 2x, times the height, which is just x. And to finish out, I guess, part A, we'll come over there and we'll write there. But let's multiply this together. If I can kind of distribute the 3 at once, 7.5 times 10 is 75, but then times x, so 75x. Outsides, 7.5 times 2 would be a negative 15, and then that'll give you an x, but then again times x is x squared. Insides would be a negative 10x squared, and last would be a positive 2x cubed. Okay? And if we want to combine like terms then, and we can write our general formula over here. So volume is going to be 2x cubed minus 25x squared plus 75x. And out of this whole problem, that was the hardest part to get, was just to realize to cut basically our length, cut it to 2 equal pieces, but you've really got to focus on the volume of a box when it's actually created into a box. Okay? Now part B says let's just focus on finding the domain for this whole thing. To find the domain, I'm going to look at the volume in its factored form. So I'm going to come over here and look at it in this factored form. Obviously, each piece has to be positive. So looking at 7.5 minus x, then that part right there, in order to keep this positive, it's saying x has to be less than 7.5, right? And we don't want it exactly equal to 0, so I'm going to say strictly less than 7.5. I don't want to say less than or equal to, because then that's telling me that if it's equal to 7.5, then my length is 0, and how are you on earth are you going to find the volume of a box that has no length? So let's just go strictly less than that. If we go to the middle equation, where we have 10 minus 2x, okay, then that's saying right there is I need that to be positive. So then in that case, x has to be less than 5, but in both of these we need to keep them obviously greater than 0. So if I plug in 5, you get 10 minus 10, which is 0, and not going to work. So again, non-inclusive there. Okay, so if the first one says I can go all the way up to 7.5, but the second one says nope, I can't even go quite that far, I have to stay at least within 5, then there's your domain. Your domain is just going to be the interval from 0 to 5, and definitely not including 0 and 5. Okay, part C. In part C, it's asked us to use a graphical method to find the maximum volume and then the value of x that gives it. Okay, so basically, in other words, use a graphical method. We can go to our graphing calculators if we wanted to, or if we wanted to find it out by hand, what I could do is just take this volume equation, which is part A, pull out the common x, which was going to leave a parabola, and then try to find the vertex through that. Or we can just get out our graphing calculators and graph it that way. So why don't you pause it for a second, let's pull out our graphing calculators, and I want you to plug in the volume equation and ask it to find the max for us. And let's come back and compare our answers. Okay, so hopefully y'all did what I did, where I just plugged in y equals just the 2x cubed minus 25x squared plus 75x. Plugged that into my calculator, and then I just had it calculate for me the maximum point, and it gave me the coordinate of 1.9666.02. So interpreting that a little bit, it just basically says that my x value, so in those pieces that I'm cutting away, is about roughly 1.96 inches, then I get a maximum volume of 66.02 inches cubed. Alright, and then in part D, we just want to confirm our results analytically. So we want to see if this actually does get it. Let's take the derivative of our volume equation. So dv dx is going to be 6x squared minus 50x plus 75. Okay? If I set that equal to 0, to try to finish solving this out and to see if it works, you get 0 is equal to 6x squared minus 50x plus 75. Alright, so what we're going to test to see if really that 1.96 is going to be our value, it's our critical point. Let's just plug that in so we don't have to worry about factoring. So let's plug in right there a 1.96. Let's plug in a 1.96 right there. There might be a little bit a rounding error, obviously, because we had to truncate that, but let's see if we get, basically, when we plug it in, we get 0. Okay, so if y'all pause real quick, go check it out. When I plug it in myself, I get basically 0.05, so there's just a little bit rounding in there, but that's just saying that's definitely a critical point. And if you wanted to, if you tested it, put it in there against the derivative, say v prime, we put 1.96. If we test the number to the right and to the left, an easy number to test would be 0, because it would wipe away those two portions, and I get 75, which is positive. And if I test to the right, just anything over there, plugging it in, I will get negative. So going from increasing to decreasing, that shows that value right there for sure is a max. So when you get a x value, when you cut away an x value of 1.96, you're maximizing your volume for that box. Okay, so let's go on to the next example. Here with number 30 in the book, if I look at it, we want to find a positive number for which the sum of its reciprocal and 4 times its square is the smallest possible. Okay, so we want to find x, and here are the conditions. The sum of its reciprocal and 4 times its square is going to be the smallest possible. So I'm just going to represent, let's say, s as being the sum of the two. Okay, and if we start taking derivatives, this is going to be, first of all, x to the negative 1 plus 4x squared is equal to s. Now let's take derivatives. So it'll be negative x to the negative 2 plus 8x is equal to ds dx. And then because we want to find it specifically when it is the smallest possible, what we're looking for is a minimum value here. Okay, we want the minimum. Okay, so now to finish solving it out, in order to find the minimum value, we're going to set our derivative equal to 0. So we get 0 is equal to negative x to the negative 2 plus 8x. Let's move over x to the negative 2. Okay, I'm going to write that as 1 over x squared is equal to 8x. And then I'm going to multiply both sides by x squared, just so we can get rid of the fraction on the left. So 1 is equal to 8x cubed. And this is saying x cubed is 1/8 or x is 1/2. So right there, at 1/2, when x equals 1/2, the sum of the reciprocal and 4 times the square will be the smallest possible. And again, if you want to test just to make sure, hey, really, is it the smallest? Is it a minimum value? We want to test for that. Then again, do your critical point, test your point against the derivative. We'll test against s prime. If we go into our equation, which our equation is just right above us, and we can test, let's say, 0. Probably actually shouldn't be 0. 0 is going to be undefined, so let's go even smaller. Let's say we want to test -1, and let's test +1. Well, with +1, it's basically 8 times 1 is 8, minus the reciprocal of 1 squared. So 8 minus 1 is 7, so it's definitely positive right there. And if I go with -1, you'll basically get -8 minus the reciprocal of 1 squared. So at -8 minus 1, and it's definitely going to be negative. So since I'm going from decreasing to increasing, I definitely have a minimum, so it checks out. Okay, let's go on to the next example.